Here we're going to use desmos to simulate what's going on with the optimization problem with calculus. So first of all, I'm going to load in an image that has the details of the problem. So we've got that there. So here it is. Let's just place this up above, and you can see that the problem is basically that we've got a certain function, e cos x, and we want to look at what size rectangle we could actually house within that and what the maximum size area of that would be. So what we do is we just type in function x is equal to e to the cos x. So that does that pretty nicely, but what we can do here now is to put in a domain. So we want it to essentially just go between -3 and 3, -3x and 3. So that's pretty much all of the graph that we actually really need to look at. So we've got all the information for this. We can now get rid of that, and we could fix up our domain so we could see things a little bit more clearly, but for now we might just leave it at that, except perhaps let's get the x values set up for this properly. So our x needs to go between -4 and 4. So the graph's starting to look a little bit better. At this stage I won't worry about the y because we're going to need to look at derivatives in this situation here. So we'll have to actually look at the graph and how it works for that. Alright, so we're going to introduce a constant, and we're going to call it c, and I'm just going to make that equal to 1 to begin with. So I haven't said what that is yet. I'm going to create a point, a movable point, that it's going to have an x value of c and a y value of function c. So there's that point, and then what you can do then is move that point up and down. So that's going to be useful to us. If we want to go and change the color of that point, let's see. So if we click on here, we can go and change that in whichever way we actually wanted to. Okay, so let's go and put another point on here now, and that's going to be a point that's mirrored on the other side. So it's going to be -c and function -c. So when we move our value of c, it goes from one side to the other. Now this is going to be the top points of our rectangle in the end. So that's basically what's going on with that. We now want to create a line which is going to have this equation. So it's going to be y is equal to, and I'll have to explain this to you after we finish, after we get past this, and we want to have less than or equal to appear there. I think the only way we can get less than or equal to appearing is, yeah, there it is, less than or equal to our value for x and less than or equal to our value for c, and then we want to use a colon. I can just use my computer to type that, and function c. So let's see what that's actually done. So between -c and c, we've got function c, and it's now showing us that value as we actually go. So let's go and type in x is equal to 0 is less than or equal to y is less than or equal to function c. So, and that's going to be c. So now we're getting the sides of a rectangle that are coming off there from this point. And finally, our other line for x equals is going to be x equals, and it's going to be 0 is less than or equal to y is less than or equal to function c, and that is minus c. Okay, so what we have now is that as you drag one, it drags the other, and it shows you the actual bounds of the rectangle. So we want to get the optimized area somewhere here between 2 and minus 2, so that's what this problem is all about. So this is a pretty sophisticated example, this problem here. So, but we'll persevere with it. And well, actually at this point I might just leave it and I'll just show you what the answer is, what we're heading towards. So what we're heading towards in the end is this solution. So if I open this up, you'll see here that this is your basic rectangle, and we're looking for the maximum area, and the area turns out to be this. And basically it's calculated by just using 2 times the c value, which is the x value, so it's double the c, so 2 times c times by the height. And the orange curve here is the first derivative of that, and the blue curve is the actual area function itself. So there's the area function, and the maximum occurs when the first derivative is 0, so that value there pretty much is going to be the maximum. So it just creates this really nice simulation in the end.